Picture this. Everything around you, your hands, the screen you're glued to, the chair you're sitting on, is built from just 3 tiny building blocks: protons, neutrons, and electrons. Now, let your imagination soar beyond your room, past the red deserts of Mars, through the swirling arms of the Andromeda Galaxy, and halfway across the observable universe. Guess what? It's still the same trio: protons, neutrons, electrons, making up every speck of matter as far as we can see. But here's where it gets wild. The universe is hiding a cosmic secret. It's not about what we see, but what we don't. Where's the antimatter? Why isn't the universe brimming with it, just as it is with matter? And while we're at it, why are ghostly particles called neutrinos zipping through you right now unnoticed? Oh, and there's a mystery element, lithium, that's throwing a wrench in our story of how the universe began. Buckle up, because we're diving into these cosmic enigmas, and by the end, you'll be itching to share your thoughts in the comments below. Let's unravel the universe together. Imagine a universe where everything has a doppelganger, a mirror version with opposite traits. That's antimatter. Particles identical to their matter counterparts, but with flipped charges. An electron? Negative. Its antimatter twin, the positron? Positive. Sounds like science fiction, right? But antimatter is as real as the ground beneath your feet. It's a cornerstone of the standard model of particle physics, and we've been spotting it in experiments for nearly a century. Back in 1932, physicist Carl Anderson at Caltech stumbled upon something extraordinary. Using a cloud chamber bathed in a magnetic field, he watched cosmic rays, charged particles from outer space, dance through the air. Their paths curved, revealing their charge and mass. Among them, Anderson found particles with the mass of an electron but a positive charge. He'd discovered positrons, earning a Nobel Prize in 1936 for cracking open the door to antimatter. But here's the kicker: the universe should be teeming with antimatter, just as it is with matter. Why? Because the math says so. In 1928, British physicist Paul Dirac, another Nobel laureate, crafted a quantum field theory for electrons that demanded balance. His equations predicted that every particle, from electrons to the quarks inside protons, has an antimatter counterpart. Antiquarks can form antiprotons and antineutrons, which pair with positrons to create antiatoms. You could build an entire anti-planet indistinguishable from ours until it touched regular matter. Then, boom, they annihilate each other, releasing pure energy as light. So if antimatter is so fundamental, why is our universe overwhelmingly matter? This mystery, called baryonic asymmetry, has physicists scratching their heads. Let's explore what we know. Experiments at CERN, the world's particle physics powerhouse, have probed antimatter's quirks. In isolation, antiparticles like positrons and antiprotons have the same mass as their matter twins, down to mind-boggling precision. Electromagnetically, they behave identically, just with opposite charges, as Anderson saw. But the universe isn't just about electromagnetism. There are 4 fundamental forces: electromagnetism, gravity, and the strong and weak nuclear forces. In the 1950s and 60s, scientists discovered something odd about the weak force. It's picky. Regular particles feel it only if they're left-handed, a quantum property tied to their spin, while antiparticles need to be right-handed. Even stranger, the weak force's strength differs between them, as shown in a 1963 experiment by James Cronin and Val Fitch, earning them a Nobel Prize. Could this explain the missing antimatter? Nope. The difference is too small to account for the universe's matter dominance. What about the strong nuclear force? Theories suggested it might treat matter and antimatter differently, but every experiment says otherwise. It's impartial. That leaves gravity, the force that shapes galaxies and keeps your feet on the ground. Could gravity treat antimatter uniquely, maybe even making it fall upward? It's a long shot. Galileo's legendary experiments showed objects fall at the same rate, regardless of their makeup, a principle cemented by Newton and Einstein's general relativity. But science thrives on testing assumptions, so CERN's ALPHA experiment took on the challenge. In September 2023, ALPHA published groundbreaking results in Nature. They created antihydrogen atoms, positrons orbiting antiprotons, and trapped them in a near vacuum chamber using magnetic fields. Why antihydrogen? Its neutrality minimizes interference from stray electromagnetic forces. The setup was a marvel. Millions of positrons from a radioactive sodium isotope were cooled, guided, and merged with antiprotons, made by by slamming protons into metal. These anti-hydrogen atoms, acting like tiny magnets, floated in the chamber. When the magnetic fields weakened, the atoms escaped, either upward or downward. If gravity pulls antimatter down, more should exit the bottom. If it repels, more would go up. The results? About 75% of anti-hydrogen atoms escape downward, suggesting gravity pulls antimatter just like matter. But the gravitational acceleration measured was 0.75 g, where g is Earth's gravity, 9.8 meters per second squared, with error bars of plus or minus 0.13 g and plus or minus 1.6 g due to experimental uncertainties. This means 1 gram is still plausible, ruling out wild theories of antimatter falling upward. So antimatter isn't weird enough to solve the baryonic asymmetry puzzle. The weak forces differences are real but insufficient, and no other force seems to care. Are we missing new forces or particles that tilt the scales? Or is the universe's matter dominance a cosmic fluke? Drop your thoughts in the comments. Do you think there's a hidden force at play, or is it just chance? Let's dive deeper into the antimatter enigma, because this mystery isn't just about missing particles. It's about why we exist at all. Imagine the early universe, a seething cauldron of energy where matter and antimatter should have been born in equal amounts. According to the standard model, every time a particle popped into existence, its antiparticle twin should have too. These pairs would collide, annihilating into bursts of light, leaving nothing behind. Yet, here we are, in a universe brimming with matter, stars, planets, you, me, and barely a whisper of antimatter. This imbalance, known as baryonic asymmetry, suggests something tipped the scales in matter's favor during the universe's first moments. One theory, called CP violation, proposes that certain processes in the early universe slightly favored matter over antimatter. The weak forces quirks, as Cronin and Fitch showed in 1963, hint at this, but the effect is too weak to explain the full disparity. CERN's ongoing experiments, like those at the Large Hadron Collider, are hunting for undiscovered particles or forces that might reveal stronger CP violations. Could a new particle, perhaps tied to dark matter, hold the key? The stakes are cosmic. Solving this could explain why the universe didn't annihilate itself into nothingness. What do you think? Could a hidden particle be the hero of this cosmic drama? Share your wildest theories in the comments. Now, let's pivot to something even stranger, neutrinos, the universe's ultimate introverts. These fundamental particles, part of the lepton family like electrons, are nearly massless and neutral, dodging most interactions. They zip through you, trillions per second, yet there's only a 1 in 4 chance one will bump into an atom in your body over your entire life. Neutrinos interact only via the weak nuclear force, earning their ghost particle nickname. Most come from the sun's nuclear fusion, but others hail from cataclysmic events like supernovae or black holes. Unlike photons, which take 1 million years to escape the sun's core, neutrinos zip out in 2 seconds, traveling near light speed. Catching these elusive particles requires an extraordinary telescope, and that's where the IceCube Neutrino Observatory comes in. Buried deep under Antarctica's ice at the Amundsen-Scott South Pole Station, IceCube isn't your typical telescope. It's a cubic kilometer of ancient ice laced with 5,160 light detectors, called digital optical modules, strung between 1.5 and 2.5 kilometers deep. Why ice? When high-energy neutrinos collide with ice atoms, they spawn muons, particles heavier than electrons. These muons, moving faster than light, travels in ice, not a violation of physics. Light slows in dense materials, create a shock wave of blue light called Cherenkov radiation, like a quantum sonic boom. IceCube's DOMS catch this glow, triangulating the neutrino's path back to its cosmic origin. Building IceCube was a Herculean feat. Over 7 years, from 2004 to 2010, scientists drilled 86 holes, each 2.5 kilometers deep, using 18,000 liters of fuel per hole to melt 750,000 liters of ice. Work paused each Antarctic winter, resuming only from November to February. The result? A telescope in one of Earth's harshest environments, capturing a terabyte of data daily, with hundreds of gigabytes beamed via satellite to researchers worldwide. Most detections are cosmic rays, 275 million daily, but neutrinos are rarer, with about 275 caught each day. Of the 100,000 annual neutrino detections, most arise from cosmic rays hitting Earth's atmosphere, not deep space. But on September 22nd, 2017, IceCube hit the jackpot. A burst of Cherenkov radiation traced a high-energy neutrino to a blazar, a supermassive black hole in a distant galaxy spewing particle jets toward Earth. This detection triggered a global alert, directing telescopes to the source, marking a new era of multi-messenger astronomy. Neutrinos, unlike light, cut through cosmic obstacles like dust or magnetic fields, offering a direct view of extreme events like supernovae or neutron star mergers. IceCube's data helps physicists test theories about neutrinos, dark matter, and even the ice itself, pushing the boundaries of our cosmic understanding. Want to geek out over neutrinos? Drop a comment about what cosmic event you'd love IceCube to catch next, and hit that like button to keep the science vibe going. Now, picture yourself standing on the icy expanse of Antarctica, the wind howling at -50°C, unaware that beneath your boots lies a telescope unlike any other. The IceCube Neutrino Observatory, operational since 2010, is a marvel of human ingenuity, capturing neutrinos from the universe's most violent events. These ghost particles are so aloof that they slip through entire planets without a trace, but when they do interact, they create a spectacle. IceCube's 5,160 detectors, suspended in crystal clear ice, catch the blue glow of Cherenkov radiation from muons spawned by neutrino collisions. Each detection is a breadcrumb leading back to cosmic cataclysms. Think exploding stars or the fiery jets of blazars. In 2024, IceCube reported detecting 1,200 high-energy neutrinos from extragalactic sources, a record that refined our map of the universe's most energetic regions. This telescope doesn't just look at the sky, it sees through it, revealing secrets light-based telescopes miss. The data, streamed at 300 gigabytes daily to global researchers, is fueling discoveries about neutrino oscillations, how they morph between flavors, electron, muon, tau, and even probing dark matter's elusive nature. Want to geek out over neutrinos? Drop a comment about what cosmic event you'd love IceCube to catch next, and hit that like button to keep the science vibe going. Let's zoom back to the universe's birth. The Big Bang Theory paints a vivid picture. 13.8 billion years ago, all energy was squeezed into an infinitely hot, dense point. A singularity, then bang, the universe expanded. Within a second, it cooled to 10 billion degrees Celsius. Still too hot for matter to form. By 100 seconds, at 1 billion degrees Celsius, protons and neutrons began binding into hydrogen, its isotope deuterium, and helium. Rarely a third proton joined, forming lithium, specifically lithium-7, with 3 protons and 4 neutrons. The math predicts the early universe was 76% hydrogen, 24% helium, and a tiny 0.000007% lithium-7 by mass. Spectroscopy of stars today roughly matches this. Our sun is 71% hydrogen, 27% helium, and 2% heavier elements, tweaked by billions of years of fusion. But lithium? It's a problem. We see 3 times less lithium-7 in primordial stars than predicted. Even weirder, lithium-6, 3 protons, 3 neutrons, supposedly ultra rare, is 1,000 times more abundant than expected. This discrepancy, studied intensely in 2025 by the European Southern Observatory's extremely large telescope, challenges our understanding of nucleosynthesis, the process that birthed elements in the universe's infancy. One hypothesis suggests that early stars, or population 3 stars, devoured lithium through fusion, skewing the ratios we observe. Another posits that unknown particles like axions meddled with the Big Bang's nuclear reactions. The James Webb Space Telescope in 2025 detected lithium signatures in galaxies 13 billion light years away, yet the data still doesn't align perfectly. This puzzle isn't just about lithium, it's about whether our model of the universe's birth needs a rewrite. What's your hunch? Is the Big Bang model flawed, or are we missing a cosmic process? Let's debate in the comments. Let's zoom out to the lithium puzzle, because this tiny element is shaking the foundations of our cosmic origin story. Lithium, with just 3 protons, is one of the universe's primordial elements, forged in the Big Bang's first minutes. The hot Big Bang model predicts a specific recipe: 76% hydrogen, 24% helium, and a trace 0.000007% lithium-7 by mass. But when we peer at the oldest stars, their light tells a different tale. Lithium-7 is 3 times scarcer than expected, and lithium-6, a less stable isotope, is bizarrely overabundant. This discrepancy, studied intensely in 2025 by the European Southern Observatory's extremely large telescope, challenges our understanding of nucleosynthesis, the process that birthed elements in the universe's infancy. One hypothesis suggests that early stars, or population 3 stars, devoured lithium through fusion, skewing the ratios we observe. Another posits that unknown particles like axions meddled with the Big Bang's nuclear reactions. The James Webb Space Telescope in 2025 detected lithium signatures in galaxies 13 billion light-years away, yet the data still doesn't align perfectly. This puzzle isn't just about lithium, it's about whether our model of the universe's birth needs a rewrite. What's your hunch? Is the Big Bang model flawed, or are we missing a cosmic process? Let's debate in the comments. Transitioning to a broader view, let's ponder the tools we use to unravel these mysteries. The universe is a vast laboratory, and our telescopes, whether optical giants like the Vera C. Rubin Observatory or IceCube's icy array, are our microscopes. In 2025, the Rubin Observatory began its legacy survey of space and time, scanning the sky to map billions of galaxies, hunting for clues to antimatter's absence and lithium's scarcity. These observatories don't just collect light, they capture stories. Stories of particles born in the Big Bang, of neutrinos fleeing black holes, of elements forged in cosmic fires. But they also reveal our limits. Neutrinos, for instance, are so hard to detect that IceCube catches only a fraction of the trillions passing through it daily. Antimatter experiments at CERN require precision so extreme that a single stray photon can ruin a measurement. Yet every data point brings us closer to truth. The 2025 Nobel Prize in Physics, awarded to researchers advancing multi-messenger astronomy, underscores how combining neutrinos, light, and gravitational waves is revolutionizing cosmology. How do you feel about humanity's quest to decode the universe? Share your thoughts below and subscribe to join our cosmic journey. Now, let's get philosophical for a moment. These mysteries, antimatter's absence, neutrinos' ghostly dance, lithium's shortfall, aren't just scientific puzzles. They're windows into our place in the cosmos. Why does the universe favor matter, allowing stars, planets, and life to form? Why do neutrinos, so indifferent to matter, carry secrets of the universe's most violent events? And why does lithium, a humble element in your phone battery, challenge our story of creation? These questions push us to confront the unknown, to embrace the humbling vastness of a universe that doesn't owe us answers. In 2025, breakthroughs like the Alpha experiment's gravity measurements and IceCube's neutrino detections remind us that science is a marathon, not a sprint. Each discovery builds on the last, from Anderson's positrons in 1932 to Dirac's predictions and beyond. The universe is a puzzle with missing pieces, but every experiment, every observation adds a fragment to the picture. Finally, let's wrap with a call to wonder. The universe is a story written in particles, forces, and mysteries that defy imagination. Antimatter, neutrinos, and lithium are just threads in a tapestry that spans 13.8 billion years. As we speak, CERN is planning upgrades to its antimatter facilities, aiming for even preciser gravity measurements by 2027. IceCube's team is exploring an expansion, IceCube Gen 2, to capture 10 times more neutrinos by 2030. And telescopes worldwide are refining lithium measurements, hoping to crack the Big Bang's code. These efforts aren't just for scientists, they're for all of us, chasing answers to where we came from and what we're made of. So, let's keep the spark alive. Hit that like button if these cosmic mysteries blew your mind, share this video with a friend who loves a good puzzle, and subscribe for more dives into the universe's deepest secrets. What's the one question about the cosmos you're dying to have answered? Tell us below, and let's unravel the universe together. Let's take a step back and weave these mysteries into the grand tapestry of the cosmos. Antimatter, neutrinos, and lithium aren't isolated riddles. They're threads in a vast cosmic web, each tugging at our understanding of the universe's origins and evolution. Consider this. The scarcity of antimatter might hint at processes in the Big Bang's fiery crucible that also influenced lithium's formation. Neutrinos, with their ghostly ability to pierce through matter, could carry clues about the extreme conditions where these imbalances arose. In 2025, researchers at the Simons Observatory in Chile reported new data on the cosmic microwave background, the universe's oldest light, revealing tiny fluctuations that might reflect the conditions where matter outpaced antimatter. These fluctuations could also affect nucleosynthesis, potentially explaining lithium's odd ratios. Meanwhile, IceCube's neutrino detections are mapping high-energy events that test theories of particle interactions at energies far beyond CERN's reach. This interconnectedness is thrilling. Solving one mystery could unlock others. Imagine if a single discovery tied antimatter's absence to lithium's scarcity. What connection between these cosmic puzzles excites you most? Drop your ideas in the comments and let's keep exploring the universe's hidden links. Now, let's zoom in on the human side of this cosmic chase. The quest to unravel antimatter, neutrinos, and lithium isn't just about particles, it's about our relentless drive to understand the universe. Scientists at CERN, enduring years of meticulous experiments, wrestle with antimatter's fleeting nature, where a single collision with matter sparks annihilation. In Antarctica, IceCube researchers brave brutal winters to maintain a telescope that captures whispers from the cosmos, and astronomers peering through telescopes like the James Webb chase lithium's faint glow across billions of years. In 2025, the global scientific community celebrated the launch of the Square Kilometer Array, a radio telescope network poised to probe the early universe's chemistry with unprecedented detail. These endeavors demand patience, ingenuity, and collaboration across nations. They remind us that science isn't just about answers, it's about asking bold questions even when the universe seems reluctant to reply. What inspires you about humanity's pursuit of these cosmic truths? Share your thoughts below, smash that like button if you're awed by our cosmic curiosity, and subscribe to stay in the loop for more universe unraveling adventures.